Synchronous motor starting. Dear friends, synchronous motor is not a self-starting machine. For example, you've got a motor here, and then here is a electric circuit breaker, and then it is connected to today's network L1, L2, L3, 3-pole circuit breaker, and then here's a motor, just like an induction machine, let's say, star connected. Here's the shaft, and then you want to start it up. Now it's at standstill. There is no rotation yet. You know that there is another port, magnetic field port in rotor. Here is the rotor circuitry. Let's write the terminals U1, V1, W1 for the three-phase AC connection. And then here are excitation terminals, which are F1 and F2. And you apply some external DC. Let's say here's a simple controller. Let's say RF field controller of motor. And here's an external DC supply represented by a simple battery here. And then here you have an adjustable field current. Ladies and gentlemen, when you switch on circuit breaker, when you apply power to the machine armature, you apply three-phase to UVW. You can imagine rotating magnetic field and suddenly starts, because there is no mass in rotating field side. There is no mass. When you apply electric power, there is sudden speed increment, and it rotates at the speed of ns, which is 60 f over pole pair number. That is the rotating speed of rotating magnetic field, rotation speed. But what about the rotor? Let's examine it. It is here. Assume that synchronous speed is 3000 rpm. That is just a sketch to understand what is happening inside the machine. In fact, you know, here's armature, a machine armature or stator, and when you apply three-phase AC to armature winding, here there is a rotating magnetic field. Let's say machine has 2 poles and one pair of pole, and the synchronous speed is, let's say, 3000 rpm. Here you see rotating magnetic field speed is 3000 rpm. And then let's apply some DC here. When you apply DC field current to rotor, there is a magnetic polarization. Let's say it's like this. It is such an instant that S pole, opposite pole of N, will be attracted by N pole. It looks like this. But in the operation, it was in the standstill position. There is no speed yet. So after a short while, a few milliseconds later, for example, rotating magnetic fields runs out, runs faster. So here would be S pole and here would be at M pole, because it is already running at the constant speed of ns. Now rotor is again about at the same position. Now it is repelled, as you see, repelled. Now then again it continues. A stator's rotating magnetic field runs at a very high speed, so rotor tries to catch, it will be attracted and it will be repelled, and then it will be attracted and then it will be repelled. So net torque in rotor will be, or is, surely yes, is 0. Rotor cannot move, cannot start up gaining speed, cannot start. It just vibrates, it just vibrates. But it's in vain, it's a problem. You apply some electric power to a system to rotate. Here's a motor, you apply some electric power, let's say some active and reactive power perhaps. You apply, again you apply some field here, you apply again some DC power here, here is some heat, and then again here are some copper losses in armature, but there is no output. There is no output. So it is a dangerous case. It is a kind of failure. Machine is already out of synchronization because it hasn't been synchronized yet. It is out of synchronization. There will be no energy conversion. There will be no mechanical output. But yes, there are some electrical inputs. So machine will be overheated, will be damaged. So that's a kind of failure. That's a kind of failure. Machine must not be operated under out of synchronization conditions. It is a bit dangerous electrically. Okay, how can we manage starting? So, synchronous motors are not self-starting machines. That is its natural situation. Naturally, they cannot start up itself. That is the problem we want to overcome. Okay, there are some methods can be used for starting purposes. They are, for example, we can reduce external electrical frequency by using another device. For example, a power electronic inverter would be, and then we synchronize machine at a lower speed. Let's see. Assume that here's a variable frequency inverter. Here is today's AC grid, AC network. That is a power electronic device. In fact, you remember perhaps in this flow from here, you apply AC. AC will be converted into DC, intermediate voltage or current. Here is intermediate voltage or current. Now I draw intermediate voltage type converter, inverter. And then that DC will be converted into a new synthesized three-phase AC. Here you see the voltage output, let's say new F voltage new and F new. will be synthesized here inside the new power electronic device you have introduced to the system. Let's say new frequency. You know, rotating magnetic field speed is 60 F over pole pair number. Now, please substitute F new right here. So, synchronous rotating magnetic field speed will be easily changed by changing frequency. So, assume that frequency is very low, let's say 5 Hz, 10 Hz, and then there is a very slow rotation. First, reducing frequency, start up, or sometimes we say starting methods for synchronous motor. Okay, first, as a first method, we study on reducing applied frequency. Now, assume that here is only a few rotation. Here is only a few rotation. Now, here's an observer. Assume that. Please tell the story. What you see right now. What you see. And an observer sitting on this pole says that there is a magnetic rotation around me, but it is very slow right now. So when you apply excitation to the rotor coils, DC field current, then there is a sudden locking. We lock or synchronize those two magnetic fields at a lower frequency. So synchronization will be managed or done in a lower frequency, let's say 5 Hz, in a very low frequency. But in such a case, perhaps you remember from induction machine startup or speed control methods, here is an equivalent circuit of synchronous machine. Let's say array is neglected. Here is terminal voltage, here is EF, and then EF is function of blah blah flux blah blah frequency, beep, beep, directly related with the rotation of the rotor speed, NA, KW. Since you decreased frequency, EF will decrease. Since you have decreased frequency, this term you know 2 pi f ls. So since you decrease frequency, this element will be decreased. So during low frequency startup process, terminal voltage will be decreased appropriately. I mean, terminal voltage over frequency must be kept constant. Let's say 400 volts, for example, over 50 Hertz, that is the 50 Hertz, that will be the rated values or nominal values of the machine. And then when you apply 5 Hertz here must be 40 volts. The ratio must be constant to keep overcurrent here. Otherwise, there will be overcurrent. That is an approximate method. In fact, it is not exactly like this. It is called as scalar control in the field. Scalar control, called as scalar control of any machine, because that is a scalar function. Terminal voltage over frequency is a scalar. You apply some control to keep it constant. So that's enough for this method. Now let's make a summary what we have done. in this method, we have introduced a new device, power electronics device, and then we converted a new frequency, but by this process we keep voltage over frequency ratio constant. Then we start from a new frequency, let's say 5 Hz. It is not a fixed point you decide with respect to machine type. It is not a problem. It would be 0 or 5, it would be perhaps 10. It depends on machine science and experiment. You start from 0 and then up to rated, which is, for example, 50 Hz frequency, and then you look and synchronize the system at a lower frequency, and then when it is locked at the lower speed here, and then it will be started up to a higher speed by changing frequency appropriately. You increase frequency, machine speed will increase. So here's a note. Is it possible to adjust speed by using the same method? Yes. Any operation causing change in synchronous speed will cause rotor speed adjustment, will cause rotor speed control. Synchronous speed, which is rotating magnetic field speed, is 60 F over Pope number. So you apply any frequency after locking synchronization process, and then you change frequency. Since rotor is synchronized or magnetically locked to rotating field of stator, they move together synchronously at a new speed coming from new frequency. So the frequency will be adjusted. But again, you like this method, for example, machine speed, let's say F nominal is 50 Hz, let's say, and then you wanna increase speed by changing frequency, let's say 100 Hz. Is it possible? Yes, it will be possible, but there will be some mechanical problems because speed causes some centrifugal forces. Machine rotor must stand those centrifugal forces. It would be dangerous for machine rotor. It depends the construction. For example, any salient pole machine must not be forced to a high speed because diameter is very large. Since diameter is very large, tangential forces will be very large, and centrifugal forces will be dramatically large, and that centrifugal forces will damage the rotor. That's another problem, mechanical problem. But Houston, there is another hidden problem. If rotor frequency, new frequency, is over rated frequency, which is 50 here, if it is like this, in such a case, voltage over frequency ratio not kept constant. Let me explain it here. Okay, ladies and gentlemen, you are in a mechanical system right now. Mechanical power, mechanical torque, and angular speed of the shaft. And now you adjust mechanical speed. But as you see, let's say here is 100 kilowatt output That is the rated mechanical output. But since you changed speed, mechanical output power will be changed. For example, if you substitute 0.5 50% of its rated mechanical output speed, rated output will be 50 kilovolts at most. It is directly proportional. You spend too much money, but you got only 50% output. When you adjust speed, that is a natural phenomenon, that is physics. But what about torque, Houston? Torque is proportional with forces, and you remember BIL, simple equation. B is generated in rotor, let's say, main magnetic field, and then current comes from stator, and then if you can manage to keep those two parameters constant, torque will be constant. Okay, I assure you that if you keep IF constant, B is approximately constant, and then if you keep voltage over frequency constant, I1 is approximately will be kept constant. And then here you see, by having such a converter here, I said voltage over frequency ratio must be kept constant. During such a process, in fact, you keep generated torque constant. That's it. You lost some output power, but you have managed to keep, let's say, rated torque at a constant value. You keep the torque. God bless you. You cannot keep output power constant because you cannot increase torque. For example, if you managed speed decrease here and then let's say double torque output, in such a case mechanical output would be kept constant, but there will be saturation, gentlemen. If you increase field current to increase magnetic field, there will be saturation. Cannot be managed. And then if you want to increase I1 to keep product, here's a product, B times I. If you want to keep product constant, you can increase I1, but Houston, it's a design. It's a design. You have decided whether the conductors are having such a cross-section area or have such a cross-section area. It is fixed. After you have manufactured the machine, the current or current density has already been fixed. So it is not possible. You cannot increase torque due to overheating. Here would be overheating. Here would be saturation. So torque increase cannot be managed. So output power cannot be kept constant. So what is happening so far? So far, take care. Let's say here is a rated frequency, rated nominal, rated frequency, and let's say here's torque. We prefer field frequency adjustment. We keep voltage over frequency ratio, excuse me, Here's voltage over field ratio. We keep it constant till rated frequency. During that region, machine produces constant torque. Constant torque region. But you keep constant torque at its rated value, and then you apply some speed change. Here is the power, mechanical output power. Now, take care, ladies and gentlemen. You have reached the rated frequency, so here is rated speed, nominal speed, and then machine has reached nominal output power. Here is the rated power point, rated power point. And then you'd like to increase frequency to increase speed. When you increase speed and try to keep torque constant, let's say, here is something overridden. Here is K. K will be larger than 1. Machine power limit will be exceeded. Machine will be overridden. There's a problem. You got a 100 kilowatts machine, and then you try to operate it at 120 kilowatts. It is not possible, gentlemen. There will be overheating. There will be overheating, and machine isolation or other properties will be damaged. After that point, machine torque must not be kept constant at its rated value. Torque must be reduced. And that region called as constant power region. Constant power region. When you operate under the rated frequency, machine will be operated in constant region to keep at least torque constant. And then when you operate machine over rated frequency, rated torque cannot be kept constant, otherwise machine power limits will be exceeded. You should decrease voltage over frequency ratio. We decrease here, we decrease voltage over frequency ratio because we lose torque control, because machine limits will be exceeded. Operation over rated frequency, in such a case we keep only output power constant, so we reduce that ratio appropriately on such a curve. Okay, that's enough for speed control and starting by using reduced frequency. Okay, there will be some other methods. For example, here would be an auxiliary. Let's say here's a auxiliary generator. Auxiliary generators. Instead of inverter, this setup is a rotating converter. Rotating converter, adjusting frequency and voltage over frequency. That is a mechanical converter. For example, here is a DC motor. You don't know how does it operate, but you apply some mechanical power here, and then that mechanical power will generate some electric power here, that electric power parameters, frequency and voltage will be adjusted by field current of auxiliary generator and the speed of auxiliary generator, and you can keep voltage frequency ratios constant in appropriate regions, or you can change frequency easily by adjusting the speed of auxiliary DC driver here. And then instead of connecting that motor to network directly, first of all you connect the motor to the auxiliary generator system by switching K1 on, and then you start motor up to its rated speed, and then when machine reaches its rated value here, then the auxiliary system will be opened, key 1, and this side will be on. You switch off here and then on here. After starting process you do this and you directly connect synchronous motor to the network. But here's something vague, because there must be some checkouts, synchronization requirements must be satisfied before K closed. Here's the K, because you know phase sequence must be equal, zeroth condition, voltages must be equal, frequencies must be equal, there must be no phase difference between those two phasor systems here and here. So there are lots of problems. It is not very easy, but that method in the history is used. For example, that is a rotating auxiliary generator starter. You set up such a starter, one starter in a factory, that is the auxiliary bus, and then assume that there are lots of synchronous motors in a factory, and then you decide one to start, so you choose K1, start it up and then connect to network, and then you want to start another motor, again connect auxiliary system and then start it up and then connect it to directly to the network. But it is not used right now. What you can perhaps see in the old setups, that is another method you can manage. Okay, we have discussed reducing electrical frequency. You can also start machine by using external prime mover. Sometimes it is called as pony motor. Pony motor. In fact, let's find the driving by using an external prime mover. In such a setup, generally a prime mover, a pony motor, let's say pony, burada ufak bir motor anlamına geliyor. Pony motor will drive the synchronous motor. You drive motor by using another motor. It looks like funny, but the problem is different. When you switch on K1, here is a rotating magnetic field at the speed of ns, but machine cannot locked up, cannot be synchronized. So to manage this, you increase shaft speed close to ns before switching K1 on. What we are doing, here's a DC motor, which is pony motor. It would be any kind of motor. In fact, there would be some diesel engine, for example, or a gasoline engine, it doesn't matter. Something to drive you need. So you adjust field current, you manage speed control here. That speed will be adjusted to synchronous speed, and then Again, come back here. Here's rotor. You applied DC. There's a magnetic polarization in rotor. And there is no speed difference between rotor speed and stator's rotating magnetic field speed. They are approximately close to each other. So, when you apply electric power to the stator, synchronous speed appears and they are locked together suddenly. Since they move at the same speed, there is a jump locking process. There will be some transients. Not to have transient currents here, synchronization requirements must be met, must be satisfied before closing K1. That is must. Always synchronization must be checked if it is okay or not. Pony motor we have examined. There will be some diesel motor, induction motor. And now someone can confuse. Let me write it down here. As a second method, use a pony motor, which is an external mechanical prime mover. Prime mover tahrik makinesi demek. Now, here is motor, synchronous motor. You want to drive a mechanical load. Gentlemen, here's a mechanical load. You use synchronous motor to drive mechanical load. And on the shaft right now, here is again the shaft is continue. Assume that it is continuing. Here's a pony motor, pony auxiliary motor to drive it up. Now, in case they are connected together or a mechanical load cannot be adjusted, assume that in case such a not adjustable mechanical or not be separated mechanical load here, in such a case pony motor must have a power as high as synchronous motor. That would be very large. It costs too much money, ladies and gentlemen. There is a problem in your design. So, to use such a pony motor startup method, here must be a clutch, mechanical clutch, or load must be adjustable. Mechanical clutch burada debriyaj sistemi olmuş oluyor ya da yük ayarlanabilir olacak. So, here must be low mechanical load, as low as possible. If it is very low, so here you need very small pony motor. If it is a high power mechanical load here, so pony motor will be large and it costs too much money. Economy is always constrained because we have limited money, you know. So to use pony motor startup method, there must be a mechanical clutch or adjustable mechanical load before starting. Otherwise, these small size motor cannot speed up the system. So those kind of methods are not suitable for every application. Some applications will be appropriate for this. Okay, so let's continue on the third method. In fact, I have already mentioned about this. Remember, there were amortisseur windings in the system, or we call damper windings. There were two purposes. One is damping oscillation, but in motor we use damper windings or amortisseur windings for startup purposes, for starting. Okay, how it would be, let's check it out. Starting by using amortisseur windings, let's say starting by using damper amortisseur, another damper winding. It looks like induction machine startup because you see, let me get it closer. You see some short circuit bars inserted into appropriate slots. Here are short circuit bars, just like in squirrel cage induction machine rotor. Here are short circuit rings. Here is another one because there are two rings, and those are, you know, short circuit bars. They are short circuited in each side. That is a kind of squirrel cage, sincap kafes, squirrel cage, just like what it was in induction motor. First, apply RST, I mean three-phase, to UVW, to stator, and then NS will appear, and then motor starts to speed up asynchronously. Okay, remember induction machines theory. Rotor speed in induction motor is approximately close to synchronous speed in stator, rotating magnetic field speed in stator. So machine rotor will tend to catch synchronous speed, but you remember rotor speed is always less than synchronous speed in induction motor, but it is approximately equal, especially in no load case. Again, if there is a mechanical clutch or a very low mechanical load during the startup, so rotor speed will be very close to synchronous speed. And then as a second operation, apply DC to rotor. Before applying DC, what is happening inside the machine? Let's imagine. Now you have applied three-phase AC to three-phase stator, and then there is a rotating magnetic field, and then due to squirrel cage construction in rotor, machine has started up, speed up, close to synchronous speed. Let's say stator's rotating speed is 3000 rpm, rotor is less than, but it is approximately close to 298 or 9, let's say 80. There's a difference, but it is approximately close rpm. Rotor get an asynchronous speed. Now here is an observer and reporting the case right now, and we ask observer, what is the case in your situation? Observer answers, Yes, I move such a speed, high speed with respect to earth. You see, okay, that is the speed with respect to earth, ground, and then above me there is a rotating magnetic field. It rotates at 20 rpm, Papa, 20 rpm. Revolution per minute. There's a 20 rotation with respect to rotor's position in a minute. So there is a very slow change in rotation with respect to observer, with respect to rotor. When you apply DC right now to rotor, those two systems will be locked, synchronized to each other, then synchronized will be managed. After that, machine will operate as a synchronous motor. Okay, we were here. Machine will operate as a synchronous motor. Second, apply DC. When you apply DC, synchronization will be done, and then motor operates as synchronous motor. There will be no action in damper windings after that, because they move together at the same speed. If there is no relative speed between rotor and stator, there is no current in damper bars. But in case there are some delta oscillations, in case there's a power change, there will be some delta swing, rotor position swing. In such a case, there is a relative motion of damper bars with respect to stator's rotating magnetic field. In such a case, there will be some currents here, and that currents induce some reverse torques or forces to damp the oscillations, and that usage is called as damping amortisseur action. And we have already discussed damper windings earlier, the main operating principle, how it operates, how it dumps the oscillations. We have already learned this. And the same setup or design can be used for startup purpose. In motor application, damper bars are very large. In synchronous generator application, damper bars are a little bit weaker. Perhaps we can see some other damper bars in synchronous machine images. This one is a better view. The bars here looks smaller in diameter, in size, but let's take this one. Here you see damper bars. They are much more larger. Here you see some other damper bars, very larger. And again, in our class notes, here you see damper bars, rectangular, you see rectangular shape, very deep and strong, very large bars. In motor, as an experience, we use larger sized damper bars. Okay, that's enough for amortisseur winding startup process. Of course, all the other methods used in induction machine theory will be used here, but for example, in induction motor startup you use star delta connection, auto transformer applications. Since synchron motors are very large motors, generally star and delta method is not used. there will be much more effective methods. For example, auto transformer. We generally decrease voltage by using an external device. In this case, we use auto transformer. Remember, there were soft starters in induction motor. Here would be soft starters. You are not responsible with this, but you should know how amortisseur winding startup is acting, how does it operate, how it is used. Usage is here. First apply power to stator, wait for a while for induction motor startup, and then keep mechanical load as low as possible to increase no loss speed close to synchronous speed. After reaching rotor speed close to synchronous speed, apply DC current to the rotor, and then synchronization will be done and machine operates as a synchronous motor. You should remember this. I have mentioned 3 methods can be used for starting process of synchronous motor.